We're now going to look at two example problems using the equation I equals J dot A and the equation integral I equals integral J dot dA. And the application comes down to whether you are told you have a uniform current density, in which case you will absolutely use I equals J dot A, or whether you have a non-uniform current density. And you will know you have a non-uniform current density because they will give you J as a function of R. So if you're given an equation for the current density, you will use the integral, the calculus version of the equation to calculate the current. And if it is uniform or constant, then you will use just J dot A. So as I have here, please get this into your notes because it is not really very realistic to assume a uniform distribution of electrons through the cross-section of a wire, since the electrons will want to repel each other, so we would expect a higher current density closer to the surface of the wire. And we can approximate it by looking at only current in that section, right? So that's kind of what they're doing here. So why they're getting away with using a uniform current density, because they're assuming there's no current density near the very center of the wire. So the other thing to note with all of these dot products, if for current density problems, they will not give you the angle, you are to always assume cosine of 0 degrees. So they will explicitly give you an angle to use if they do not expect you to use cosine of 0 degrees. So that takes really the dot product out of the problem. Cosine of 0 is +1. You have to calculate, you have a little bit of math to do here. You have to calculate just the blue shaded area. So shaded area only. Plug in the numbers you were given, and you can then see if you calculate the 1.9 amps. If you want to do that, pause the video, and then we can look at the solutions together later on. So attempt that one. Looking at the non-uniform current density, we will again be assuming that the dot product is cosine of 0 degrees. We will always be using cylindrically shaped wires, so the dA will always be the differential area based on the cylindrical geometry, which gives us a circular cross-sectional area. 2 pi r dr will always be the dA that we use, so that gets substituted in here. You'll simply substitute the AR in for the J, cosine of 0 degrees, integrate. Our limits are, again, we're only interested in the section of the wire from R on 2 to R. And if you do that integral and plug in the numbers, you should get the 7.1 amps. So pause the video here, see if you can finish out the math, and when you unpause, we'll take a look at the solutions together. Okay, so here we have our solutions. Again, the shaded area only. Take the full area, subtract out the center portions. That gives you only the shaded area when you plug in the 0.002 meters for the radius. Hopefully you can get the math correctly into your solution and get the 1.88 amps and round it to 1.9. For the integral, we're left with the integral of a polynomial down here. So we have the r cubed integrate increase, r to the 4th over 4. When we do final minus initial, we get our 7.07 amps. So I will zoom back out here. You can pause the video, look at the solutions. And as always, ask questions should you have them.